In the last lecture, we were discussing the intensity distribution of the interference fringes on the screen, and this is the kind of graph I showed you. And we also thought what would happen if monochromatic light is replaced by white light, and then I showed that the intensity distribution would remain similar for each wavelength, except at the center there will be colored fringes, except at the center where all colors combine to make it a white fringe. And then we also saw interference between waves reflected from an interface between two media, and we shall continue with this topic. I hope you remember this figure. We have this medium N1, this medium N2. This is the slab or a film whose thickness is T. We found the difference between these two, the path difference and the phase difference between these two waves 1 and 2, and just as 1 and 2 can interfere destructively or constructively depending upon the phase difference between them, the waves 3 and 4 can also interfere destructively or constructively depending upon the phase difference between them. And this is the basis on which anti-glare or anti-reflective coatings is made on your eyeglasses. For example, on this coating is there, which is known as anti-reflective coating. What it does is that it is a film, thin film. The fringes that you see, these colored fringes, you see in thin films like a soap film, or if there is a film of oil on a wet floor, then you will see these fringes, right, interference because of reflection. But because of reflection also there is interference, and we so this is a thin film deposited on your eyeglass, and what happens is that the thickness of this film is so arranged that only those colors which are allowed go through, the others do not. The net result is that the intensity of light decreases. The glare that you felt is no longer there. So, that is the basis, anti-glare or anti-reflective coating on your eyeglasses, and other optical instruments, they work on the same principle. The thickness of coating made of special material is so adjusted that unwanted wavelengths undergo destructive interference. Only desired wavelengths reach the eye, thus cutting down the intensity of light. Only desired. The thickness is such, the phase difference, you remember, depends upon the thickness. So, you arrange thickness in such a fashion and arrange, of course, N2 in such a fashion that the only desired waves interfere constructively, other waves interfere destructively and they go out, and you have reduced intensity, the intensity that reaches your eye. Now, let us take up the second phenomenon, which is explained on the basis of the wave nature of light. This is known as diffraction. What is the phenomenon? Let us see. Suppose you have an edge, a very sharp edge, and light is coming from this side. Normally, you would expect that this would mark the boundary between the shadow and the light. This should be completely dark and this should be bright, but that does not happen. When you look at it carefully, as scientists did, they found that there is light going into the region which should actually be a shadow region, and that they could not explain on the if light travels in straight lines. So, to explain this phenomenon of light, very little bit of light intruding into the shadow region, this phenomenon, the light intruding into the shadow region as if the light is bending around this edge, this phenomenon of bending of light is called diffraction. According to the rectilinear propagation of light, the horizontal lines touching the shadow, the edge should form the boundary between the shadow and the bright portion, but there is light in the shadow portion, and for to explain that we will need the phenomenon of diffraction. In fact, that is why the light is said to have bent round the edge, bending of light around the edge to give you light in this region which should have been shadow. So, here also the edge or the fringes or the slits must be extremely the slits must be extremely narrow, and the edges must be very sharp to see this diffraction effect. And diffraction effect is not seen only with light, it is seen with all wave motions. The condition is that the openings or the slits must have widths which are of the order or smaller than the wavelength of the phenomenon that we are going to study. If it is sound, then the opening must be smaller than the wavelength of sound. If it is something else, then the opening must be much smaller than the wavelength of that something. So, I will give you show you various examples to illustrate what diffraction really is. Suppose you are in a hall, there is a say music concert going on, and you are in a hall, and unfortunately you get a seat behind a column or a pillar. So, what would happen? Would you be able to hear? Yes, you will hear the sound, although you will not be able to see what is happening on the stage. So, you will not see, but you will hear what is happening. This is because of the diffraction of sound. The sound bends around these edges and reaches you. Now, just to emphasize what diffraction is, I have taken this slide once again. Suppose the opening is large, then what will happen? The light goes through this, and on the screen you will see a patch which is replica of this opening or this slit. However, if this slit is much smaller, this opening is much smaller and is of the order of the wavelength of light or sound or something else, then you would see a pattern on the screen, and the pattern has this intensity pattern. We shall see on little while later what this pattern looks like, but this is the pattern you will see on the screen. If you live near a water body, say if you live near an sea or say a lake or a river, and there is an opening here shown here which has the size, this opening has the same size as the size of water waves, then as water goes through this opening you will see diffraction effects. In fact, if you look at carefully, you will see these diffraction effects because of this opening. There is a something that prevents water from flowing. There is an opening and water goes through that opening. This opening has size smaller than the wavelength of the light wave, the water waves, and therefore, you have water waves diffracting on this side. So, you see the diffraction pattern on this side. You can look for more such things. If you search Google, you will see many such photographs. Where else would you see diffraction? Have you seen a halo like structure around the sun or the moon when it is covered by thin clouds? This phenomenon is also caused by diffraction. If water drops of the cloud are separated by distances of the order of the wavelength of light, the light passing through these gaps is diffracted, causing rings to be formed around the moon or the sun. You can see that here. You must have seen this phenomenon several times. You may not have noticed it, you may not have thought about this. You see, when sun and moon, they are behind thin clouds, either sun or moon, they are behind thin clouds, then you see colored rings around these bodies. What is happening is that the gap between the cloud droplets, this gap between the cloud droplets is of the order of the wavelength of light, and therefore, when the light passes through these two gaps, or in fact several gaps, then the light, there is a diffraction of light, and these rings are due to the diffraction of light. You must have seen this scene also many times. This is known as silver lining. You know, the cloud, if it is a dark one, but its boundary, so to say, is very sort of bright, looks like silver lining, and this is also caused by the diffraction of sunlight by droplets of the clouds. Then, if you are in a very thick jungle, very thick forest, so that the distance between the leaves of these trees is very small, is of the order of a wavelength of light, then you would see there is a diffraction of light when it comes through these leaves, gaps between the leaves, and you see this kind of phenomenon. A very simple way to demonstrate diffraction of light is to hold two fingers closed in front of a source of light. So, if this source of light I will take, I will keep these fingers closed, and then I will open them slightly, very slowly, and I will see between when there is a gap between the two fingers, I see dark lines. These dark lines are the diffraction pattern. You can see, you can do with this hand, does not matter, you can do with this. Keep them closed, so that nothing is visible between them, then you open them slightly, slowly, and you will see that there is these dark lines in the gap between the two fingers. This is the diffraction phenomenon. Long radio waves used for long wave radio broadcast have wavelengths of the order of a kilometer. You know, these days you do not listen to radio. Earlier times you would have stations which would broadcast at long waves, nearby stations, and the wavelength in that case is of the order of a kilometer. Imagine a small hillock with a crest of size a few tens of meters in its way. So, this hillock is in the way of these waves, and these waves have wavelength 1 kilometer. This hillock is of this size of this is of the order of say 20, 30 or even 100 meters or even 500 meters. What will happen when the waves pass through that there will be bending of light, there will be a diffraction pattern. Now, so far I have given you examples of diffraction pattern. How do you understand this? For this purpose, we go back to Huygens principle, and now instead of 2 slits, we will just take 1 slit for the time being, and each point on that slit becomes a source of secondary waves. So, each point, you can see that each point is producing these secondary waves, and these secondary waves then would interfere and give you the diffraction pattern. Now, shown more clearly, you take this point in the slit and this point in the slit at the 2 ends of the slit. You have one wave going through this, you have another wave going through this, and there is, since they are slanted, there is a path difference d sin theta between them. So, this path difference between these two is going to do the trick. If they are, say, if the light is coming parallel to, say, perpendicular to the slit, then you have waves which are going through this in the same phase. When the waves go straight, there is no path or phase difference, and they all will constructively interfere. So, let us come back to this, and now what we do is we take, say, this is a slit, we take a point just adjacent to this edge, and then a point adjacent to the halfway mark between the slit. Halfway mark is here. So, we will take this point and this point adjacent to the halfway mark and adjacent to the edge of the slit, and then the path difference between them will be d by 2 sin theta, because this distance is not d, but d by 2. So, it is d by 2 sin theta, and whenever this is equal to lambda by 2, when theta is such that delta is lambda by 2, waves would be completely out of phase, their net intensity would be 0. That means, they would interfere destructively. So, d by 2 sin theta, whenever d by 2 sin theta is equal to lambda by 2, that is d sin theta equal to lambda, then the waves will interfere destructively and you will have dark region. And you can now take, say, second point and second point here, third point here, fourth point here. I mean, you can, since these points are equidistant, we can treat them like this similar way. So, by this exercise, we can show that whenever d sin theta is equal to n lambda, we have minimum light, we have a dark region, and the intensity, we shall not derive this relation, but the intensity of the reflection pattern is found to be Airy function. Airy function is sin x by x, square of sin x by x, that is the Airy function, where x is pi d lambda sin theta. This is pi d sin theta by lambda, this is nothing but the phase difference. So, the intensity distribution is, and if I plot this intensity distribution, that is square of sin x by x, where x is this, then I get this as a function of theta, I get this. So, you can see that there is a huge maximum at theta equal to 0, and as we go away from this point, we have pattern of bright, dark regions. So, there is a huge maximum at theta equal to 0, that is the Airy function. The width of the central maximum is much larger than the geometrical width of the slit. What I mean to say is this is much larger than the slit itself. So, the central maximum is not an image of the slit. Moreover, the intensity of the central maximum is much larger than the intensities of subsequent maxima. This is much larger than this maximum or this maximum or this maximum or this maximum. This is much larger than the subsequent maxima. Notice also that the secondary maxima are roughly halfway between the minima. This is halfway between two minima. This is halfway between two minima, roughly halfway. Therefore, one can write the relation for the secondary maxima as d sin theta equal to n plus half lambda. You remember, d sin theta equal to n lambda was the condition for the minima. For secondary maxima, the condition is n plus half times lambda, where n is 1, 2, 3. Because we have approximated that the secondary maxima are between the two minima. So, halfway between the two. So, n plus half lambda gives us the secondary maxima. Now, let us see the effect of the slit width. We have been saying that the width of the slit must be smaller than the wavelength. But what happens if you slowly increase the width of the slit? I have shown by graphs here. As the width increases, width is pi d by lambda. So, as d by lambda increases, you will see what happens. This is the maximum for this graph, and then it decreases outwards. When the width by lambda is large, you will see a very narrow maximum, and in the limit of the width becoming many times the wavelength, you will have only just a point or maximum, just a thin line. You know, this width is decreasing as the slit width increases with respect to lambda, then this width is decreasing, you can see that. And when it is 2, when d by lambda is 2, then you see this narrow maximum. And if I still increase the width, then this becomes narrower, 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 and at one point it will just become one straight line, showing that the diffraction effects have vanished. But if d by lambda is small, then you can have a huge diffraction effect, very broad central maximum. In this lecture, we have seen that when light passes through a very sharp edge, then it bends round that edge, or when light passes through an opening or a slit which is very narrow. I mean, the slit has the width of the same size as the wavelength, then you have diffraction pattern. We will continue with the diffraction by two slits. We have, in this lecture we have considered one slit. In the next lecture we shall consider two slits. What happens to the diffraction pattern? And we shall also have diffraction at other wavelengths, say X-rays, then diffraction with the neutrons and electrons, and we shall also define what is known as resolving power of an instrument. And then we will go on to what is known as polarization of electromagnetic waves.